Well, g'day everyone. Welcome to another Sunday's Toolbox Tech Talk with me, Glenn Morris from the Smart Energy Lab here in lockdown in Melbourne. And I see I've got a few visitors turning up at the various streaming points. So this is going out to Facebook, YouTube and Twitter. So it's the first one for me to do Twitter as well. I'm not sure how long it'll run for on Twitter before they decide it's too long. But anyway, here we are. I really love to get some feedback. So if you're in the comments field, want to type some comments, that would be really appreciated. That way I get to answer some questions from the audience. And also, if there's any tech problems, which unfortunately in the past we have had some tech problems, so things like echo, but I think I've nailed it this time. I've done a lot of testing. So please let me know if any of those issues persist. But anyway, today my guest on Toolbox Tech Talk is the son of one of Australia's solar pioneers. He started his own software company when he was only 16 and took over the reins of his parents' company when he turned 18. So an early entrepreneur. It's my great pleasure to introduce my good friend Peter Watkinson of AERL. G'day, Peter.
Hey, Glenn. Thanks for having me. It's my pleasure to be here today. Really looking forward to having a good chat about lots of different things. We'll see what we can come up with to keep things interesting.
Cool. Now let's see if I can bring myself on screen at the same time. Here we go. Oops. Pressed the wrong button. There I am. Great. So we've got the two of us on screen at the moment. So Peter, have you locked your cat out of the room? Because when we were doing some testing, there was some cat problems.
Yes, I do have some cat problems at the moment. But don't worry, he's well and truly locked away. But I'll probably pay for that later.
Yeah, is he a bit scratchy? Does he?
Yeah, a little bit like that. I guess it's what can you do?
Cool. So how's it going in the lockdown state? Oh, whoops, I got the wrong screen up there. Not the lockdown state, the isolation state, sorry. We're the lockdown state.
I think that's probably a question for you. You're the lockdown state, yeah. And comparatively, I cannot complain. Up here, it's it's almost business as normal. So I really do feel for Victorians at the moment, and I hope that it's all resolved and normality starts to return as soon as possible. It's really kind of, I know it's very, very hard in the solar industry and in all industries down there at the moment with sort of the reduced ability to work, which is, it does pose a bit of a challenge. Up here we do have some sort of social distancing still in place, but for the most part, it's, unless you're hosting big parties or gatherings or concerts, it doesn't really affect you on a day-to-day basis. But yeah, we've still got our social distancing place at the factory, but it's certainly not playing a really active role in our day-to-day lives like it is down in Victoria for Victorians at the moment. So hopefully it comes to an end sometime soon. Fingers crossed.
Yeah, it keeps stretching out, but from my end, it sort of feels like I've been on a long-term round-the-world trip solo in a boat, and the boat being here in the office. So yeah, it's been quite weird. Yeah. But you know, we all make the most of it. I think the reason that these Toolbox Tech Talks came about because of lockdown and I'm being at home a lot, and just aware that many companies are affected by this. But for your company as a manufacturer, has it been a big deal?
Look, I think we're very, very lucky in terms of the industry that we're in, in off-grid power and battery charging. In terms of industries that are actually going to be heavily affected by this, after things start to return to normal, I think the industries that have already been heavily affected by this, we're very sheltered to a degree, especially being a manufacturer. In times of crisis, people still need power. So we have seen especially sort of a large drop off in Victoria in the recent months, but apart from that, it's been fairly stable, which is what we really like to see. As an Australian small business, that's kind of important. But yeah,
cool. Oh, well, that's good to hear. I guess just shipping stuff around the country hasn't been such a big deal, but it's the visits and the conferences that you haven't been able to go to. Yeah, we just had the Smart Energies conference and expo virtually online because, usually it's in Melbourne. All Energy's not happening. We're kind of reinventing how we meet and how we kind of network, I suppose.
Yeah, look, we're certainly very lucky to live in this day and age that we have the ability to communicate outside of just going and visiting someone in person. If this happened, I don't know, 50 years ago, not even that even, but if this happened 50 years ago, we'd be in such isolation, being stuck at home in a pandemic. It's the effects of it, I think, would be significantly worse. So in that sense, I guess we can consider ourselves lucky that we can actually move things online and stay in contact with friends and family and colleagues through the technology we have.
Okay, well, let's move a little bit towards your company and
absolutely.
The history of your company. Like I've kind of billed this as the greatest Australian solar story that hardly anyone knows about, and so maybe this is an opportunity to kind of tell the story from your perspective, from the inside.
Yeah, absolutely. So I think it goes back. I know it goes back to the late 1970s. So when my father was studying electrical engineering at UQ, on one of his semester breaks, he developed a little bit of technology for extracting basically the most power out of a PV panel through DC to DC conversion. So effectively what it allowed him to do was operate the panel at its optimal point, and then very efficiently convert that power extracted down to whatever the voltage was that he was charging, or the power was used at. So what this really did back then was fundamentally change the value proposition of PV at a time when panels were very, very expensive. And it really sort of underpinned the rapid sort of growth from that point forward of the PV industry, because it allowed, before it was sort of ridiculously expensive to actually put in batteries and panels, but this made it 30% cheaper. And anyone that's familiar with economics, 30% is a lot. So building on that, in 1984, he founded AERL, or Australian Energy Research Laboratories, to basically commercialise this little invention that he patented at the time. And I guess the rest is kind of history from that point forward. He developed a couple of new models and sort of continued to fine-tune maximum power point tracking. And then the patent expired, and it became, it's now basically every PV inverter and charge controller globally. But he unfortunately passed away in 2008. So AERL has suffered we kind of went into hibernation after that. Being an engineer and founder, a lot of the company was sort of very much dependent on him. So we had to effectively rebuild ourselves from that point on. And we've been slowly building back up over the past 10 years, or 12 years now, actually. Oh, that's terrifying. But we're really, in the past few years, we've seen quite rapid growth, and we're doing lots of exciting things now. We've manufactured the current SRX generation of MPPTs is really something special. We played catch up there for a while after coming out of hibernation, because when the patent expired, Outback came onto the market. Schneider bought up Xantrex, and then they started mass producing these other competing MPPTs, and then by the time we kind of realized what was happening, we'd fallen quite behind. We've been building the company back up over the past few years, and really getting things back into where we should have been as a market leader, given that we developed the technology originally back in 1984. So that's basically AERL in a nutshell. We do a couple of other little things like water pumping and anything high-powered PV DC related. So that's basically AERL in a nutshell anyway.
Cool. I'm just looking to see if we got any comments here. Yes. G'day, Bradley. Hey, I'll bring myself on screen. Here, where am I? Hang on, here I am. There we go. Yeah, Bradley, he's got the popcorn, the sparkling water, and he's all set for the next hour. So, yeah, it's good to hear that I can keep you entertained in lockdown. So, Bradley Patton was actually my guest the last week, I think it was, on Toolbox Tech Talk. We were talking about their Australian manufactured batteries, the Powerplus Energy battery, which I believe your products actually work very well with.
They do. We've been testing the Powerplus batteries for quite some time now, and they're an awesome little battery, especially in the way they're really filling a gap there that just it needed to be filled really for 120 volt to become quite mainstream. It was an absolute pain to wire up 62 volt cells. And it gave you sort of very limited flexibility with the amount of battery storage you could operate at 120 volt, which is it's really keeping the market from growing properly. But now that we've got a really good Australian-made 120 volt option, you can combine that with a SP Pro 120 volt and our chargers, and you've got a really good scalable. You can have a couple of modules, you can have a ton of modules. It's totally up to you. So it's really taken the limitations away from 120 volt. At this point, which is very exciting.
Yeah. So actually, this is a bit of a segue to just talking about the products that your company makes. So all we know so far is you're called AERL, and that you've been around for over 30 years.
Yep.
So is that right? 30-something years. Or was it 40-something years? No, it's 35 years.
1980. Yes, it's 35 years.
Oh, wow.
There you go.
That's pretty awesome.
I think about that for a second.
So, yeah, what sort of products does AERL make these days?
These days we make some really high-end MPPTs because that's what we started doing, so it makes sense to continue doing that. And when you've got 35 years of experience behind you, we can do some pretty cool things there with them. So that's our main product line at this stage. But we also do solar water pumping controllers, so direct drive PV to DC motors, permanent magnet motors, which is if you're running daytime water loads. That's really great because you don't have to include a battery bank. Sorry, Bradley. You don't have to include a battery bank there, which really brings the cost down on a water pumping system if you only need the water during the day, or you can get there's enough hours in the day that's basically to pump the water you need. So that's a really exciting, and it has plenty of rural applications there. We also do cathodic protection controllers, which is not really something too related to this industry, but that's been a sort of a backbone of our company over the years. But we protect large metallic structures effectively from corrosion with impressed current into them effectively. And on top of that, we have a couple of hobby products too. We participate in the solar race car event from Darwin I think it's every second year from memory. So we design a little MPPT for racing and solar cars, which is it's just a bit of fun that we have with the engineers here. And we've also just launched in the last few weeks, about a month ago now, we've just launched Earth, which is basically filling a bit of a gap in the market when it comes to DC earth leakage detection.
Oh, hold on there. So hang on.
Which is a big thing.
The name got lost then. It's called Earth Guard.
Yes, Earth Guard.
And the purpose of Earth Guard is, what was that again?
The purpose of Earth Guard is to detect insulation breakdown in DC systems. So, installing a new system, it's not really a big problem, but, 10, 15 years down the line, insulation may break down and you may end up with a hazardous high voltage situation occurring. So what the Earth Guard does is it monitors the positive and negative poles of the DC system and looks for that leakage to Earth to warn you ahead of time before it's actually a dangerous fault. So you don't come to work on service a system in 10 years and find you get a nice shock when you touch something that you shouldn't. Or that wouldn't normally be live. So that's the gist of it.
So this is actually a requirement now with our battery standard AS5139, and it's been a requirement for the PV standard for a long time.
Well, the PV standard is subject to a clause that if there's no product available on the market, it wasn't required. But now there's a product on the market, so it is required. But it was a matter of time, and we're just happy to offer a product that meets the standard and fulfills the requirement and at a reasonable price point. So that's kind of our take on that. Because someone was going to do it, so might as well do it properly.
Cool. Yeah. So that's great. So you rose to the occasion to become the first on the market, and therefore was the only product.
That's it. I got the easiest sale pitch in the world. Really, well, you have to use it according to the standards. So we've been flat stack making them recently, which is it's been quite the challenge. But we're sort of ramping up production to meet demand, which has been exciting. But yeah, so it's one of those things. But it's like, I love the product, exclusive of the standards and all that sort of stuff, because it's something that really should be in high voltage DC systems, especially with PV voltages that we have today. You need earth leakage protection there, because it could save your life or save someone else's life. When they say a homeowner comes in 10 years time and touches something in the system, or you don't want them getting a shock. And it has it as the DC voltages that we're now seeing in the PV industry. It's just such a necessity. So it's from a ethical perspective, I love the product. It's great when you look at it like that.
Speaking of voltages, what sort of ranges could it cope with?
So right now, the current model we have is up to 300 volts on the PV side. So you can have it's a little bit different than your standard voltage sort of ratings, because the earthguards are installed on the battery bus. So we currently support 48 and 120 volt batteries. If we choose to monitor from the battery bus, because it's a centralized location on the system, and with the new battery standard, you need battery DC earth fault monitoring anyway, not just on the PV side. And it's only required on non-galvanically isolated devices, which means, from that central location in a PV system, we can see out to all the PV arrays through the MPPTs, because they're all common positive or common negative. So with one device, you can monitor the whole system. So it really improves the value proposition of DC, because I know Morningstar also has a leakage detection device, but it's not sensitive enough for the Australian market, and they require one per PV string. So if you want to do a large PV system, you're spending $1 extra just to put your earth fault leakage in, and it's not even required. It's not even sensitive enough to meet our Australian standards.
Actually, that's a good lead into our next question, which was I was under the dumb understanding that earth leakage would be a walk in the park. You just do an impedance reading from the DC to earth, and if it was less than X, then you go alarm. But you tell me it's not that easy.
No, it's a little bit more complex than that, actually. I can't go into too many specifics because it's proprietary, but we had to spend a lot of time and effort actually working out how to do it on the DC side. You can do it with AC frequency quite easily. So that's why the inverters all have it built in, and they've had it for ages, is because they've got an AC source there available. But if you're doing a DC coupled system with DC charge controllers, you can't really use AC frequency too easily. So what we had to do is come up with a DC method of detecting earth faults, which is what we've done. So it requires very, very, very sensitive. It's very similar to the internal workings of a multimeter. But it's one of those things that took quite a while to get our head around and work out the best possible way to approach it. Right. Not quite as easy as we first thought, which explains why it hasn't been done in most DC products today. So we almost bit off more than we could chew, but we got there in the end.
So your EarthGuard can be an add-on to other companies' products, is that correct?
Yeah, that's it. So originally we designed it, of course, for use with our charge controllers. So it integrates, it butts up nicely against the base of our charge controllers. It has it has the same extrusion profile. So if you're doing an install with SRXs, you've got just, one SRX that's slightly longer than the rest of them. But you hardly notice it there. But we are supporting, we have a supported list in the user manual for the EarthGuard, but we're supporting third-party products as well. So your Victrons, your Schneiders, your Outbacks. The Schneider and Outback's not yet supported, but we're in the process now. We also support the Pro as well. So that's another thing that you can. So basically, when you're checking what components you can use in a DC coupled system with the Earth Guard, that's a list to refer to. There's a couple of them that we can't support because we've found they've got internal pathways to Earth, or they're a bit too leaky. Some inverters and bits and pieces like that. So we've actually had to go and make a compatibility list as a result, and inform the companies that manufacture those that they probably need to look at tweaking that a little bit.
Yeah. I think this is from a standards perspective, which is where I'm coming from.
Find everything.
We've really raised the bar in terms of protection with earth fault alarms requirements, or earth fault detection on battery sides, on DC sides. And many companies are struggling with the implications of that. And it's a case where Australia is kind of once again first to market with, or not market, first to standards with this requirement, and sort of got the rest of the world on the hop a bit. So it's great that your company can sort of help meet that requirement locally.
Yeah, no, totally. It's at first when we were dealing with earth fault detection, it was just the biggest headache. So like, can we not install our charge controllers, or what was the deal? So, but the more we sort of dug into it and realized actually what earth fault leakage detection was, the more we kind of understood, okay, that actually makes a lot of sense, and this is something that we really should be doing in DC systems. So we did at the end of the day.
Yeah, right.
That's kind of how it happened.
Okay, so you've got the Earth Guard. You of course have got your original founding product, your MPPTs. What's happening on the MPPT scene for you?
So currently we have 4 models, 2 across the 24-48 volt space, and 2 across the 120 volt space, which are really powerful little bits of kit. And we've done some pretty recent work on those in the past few months, where we've just launched a new MPPT tracking algorithm that works in real time. So what we noticed in the industry is it kind of, when we were playing our catch up, that everyone was kind of a bit complacent with their MPPT tracking, and they were using sort of what are now outdated methods, and kind of they're slower. They periodically sample. And they don't really capture changes in solar irradiance very quickly. So what we did was we have implemented what we're terming real-time MPPT tracking that responds to changes in solar irradiance in milliseconds.
Right.
So a cloud comes over, it's always maintaining. It's almost a predictive algorithm. It maintains the MPPT so quickly to make sure that you're always getting the maximum power out of your panels, rather than waiting for our competitors' MPPT hit their sample time and then try and adjust, and by that time the cloud's already half moving over and it may find the wrong end.
Peter, I might do
so that's something that we're really proud of and rolled out
at this point, explaining what an MPPT does, just in terms of an IV curve, basically. I'm going to cut to my drawing screen, which you won't be able to see. It looks like I'm ignoring you because you're coming in on a different camera looking at me.
That's all right.
But I'm not ignoring you. I'm just going over to my drawing screen, everyone. So hang on, let me bring that one up, just to kind of explain what an MPPT is. So this is my live drawing here. I used to say I feel like Rolf Harris when I do this, but not anymore. It's not a good look. So let's see if I can. It's a terrible joke, that one. So let's just see if I can bring my key on. There I am, bottom screen. And bring on another microphone so you can actually hear me. Where are we? Wrong one. Okay, so bring this other microphone over here. Too many mics in this business. Where's that one gone? Okay. That's it. Right. Boy, it's a loud microphone. I'll just turn it down a little bit. Okay, so here we are trying to do an explainer on what an MPPT is. And so Peter, I always start with just doing an IV curve. Nice and simple. Current.
Good place to start.
Current on the left and voltage across the bottom. And what we draw is kind of the load line of a PV array or PV module, and it's got this characteristic curve which has a bit of a knee along the way, and the purpose of an MPPT is to find where the sum of volts times amps equals the most power. Is that right, Peter? Mm-hmm. Okay, so I'm going to do another axis on the side here, which is power. So we've got power. And what we're trying to do is plot to find where the maximum power is. And so it turns out that when you plot along the sum of volts times amps, you find that there is a point on this curve. We call it the maximum power point, or MPP for short. The maximum power point being where the current and voltage added together give you the maximum power. However, it's not a static thing, as you well know. Current goes up and down with a radiance, voltage moves around with temperature, and to some extent a radiance as well. So it's actually a dynamic point. It's always kind of flipping around. It's not something that you can just set and forget. Like you just program the MPPT for a certain target voltage. So my understanding is generally they'll start at open circuit and track back. Is that correct?
Yes, that's how they generally do it. They ramp up the power. So effectively,
yeah. So an MPPT is kind of like a variable resistor. It can choose how much current it's drawing, and therefore the voltage in the array will start to drop as it draws more current. So it's going to track along this line here. Now it's doing this. I'm told it's called perturb and observed. That's what I've heard it called by engineers, where it changes stuff. What's that, Peter?
Perturb and observe.
Yep. So it does perturb and observe.
It's an old MPPT method.
Oh, okay, it's an old one. All right. Well, let's not use that term then. And at some point.
So that's what our competitors use. So please, no, go ahead. Use that.
Okay.
So most MPPTs on the market at the moment use perturb and observe.
Wow.
And. Go with that.
Okay, so effectively, it's changing the operating point by testing, and if it gets more power, it keeps changing in the same direction. But if it starts to get less power, it reverses and goes back the other way. So it's hunting for that maximum power point.
That's it.
So
yeah, that's it.
In terms of what you use, you say it's not perturb and observe. What do you refer to it as?
We use something called incremental conduction, which is a more mathematically complex algorithm, but it has predictive traits.
Can you say that again? Incremental what?
Predict changes. Is incremental. So it we take slight changes in irradiance, feed them into a mathematical where the MPPT point is based on what's happening with the actual. So it allows us to react, and this is happening, hundreds of times a second. So it allows us to react to the cloud coming over, which in that situation, the entire voltage of the panel will drop down. And predict it, with the drop in panel voltage, where that. And then as the panel starts to creep back up, we go straight back up to where the MPPT point is. But yeah, it allows us to very, very quickly, as opposed to just locking onto a point and then every 5 minutes or so moving up and down looking for the maximum point.
Right. Okay. So I've learned something already, that there are more effective strategies than perturb and observe.
Well, advancements in microprocessors have allowed us to do sort of more exciting things. Got more computational power there to use, so we can do some advancement. Your MPPT point rather than just sort of moving up and down the curve.
Okay. All right. So we've talked about the maximum power point tracker, which is called the Coolmax SRX. Is that correct?
That's right. Yep.
And EarthGuard, which is it initially started as an add-on to the Coolmax SRX, but actually it's available to other products that are on the compatibility list.
That's correct, yes.
But you've got one more juicy product which has been around for a long time and hardly anyone even knows about it. What's that?
That's I assume you're referring to our controllers, is that right?
Your Cathodic. I was thinking what the Cathodic protection system.
Oh, my Cathodic protection. Oh, yes. So that's, they're a fun one. Basically, we've been making those now for almost as long as the company's been around. So it's not really the same sort of the renewable energy industry, but we actually it does tie in some regard because they are being DC powered corrosion protection devices. They are powered by PV, so we provide very see electronic devices that, basically anything metallic. That's used by a lot of the infrastructure here in Australia, and we've been a long time. But it's a fun one. It's interesting, but it's incredibly complex. Corrosion protection.
Right.
But it's basically feeding current into a metal structure based on and then to a sacrificial anode to basically form the corrosion goes away from the structure you're trying to protect. And it's funny though, because cathodic protection is effectively a massive earth fault.
All right, so you won't be having an earth fault alarm on your cathodic protection.
Yeah. We ran into that recently, and that was interesting. We had to sort of consult the standards and work. How do we do this? But we eventually worked out a way. So but that was certainly a wild week working that one out.
Right, cool. So moving on a bit, so obviously you make cathodic protection, which would be for pipelines and metal structures. Your EarthGuard and MPPT. What's its focus? What part of the industry is going to be using those devices? So
primarily at this stage, and historically, we've serviced the off-grid market. So we provide MPPTs for off-grid applications. Reliability is paramount. So think of your sort of installations that you've got your SP Pros going into, and and that's mission critical. It's going to take to get out there and service it if something fails. That's sort of the market we target with our sort of high-end MPPT offerings, and we've done that for a very long time. It's got controllers from the early days, back from pre-2000s, that are still out in the field operating, and we're still sort of, as they start to fail 20 years later, we're starting to replace them now, which is just insane. Not that fantastic from a strategy point perspective, but in terms of providing a really good historical references to the reliability of our products, it's fantastic.
Right.
There's no planned obsolescence in our.
Okay, sorry to interrupt you. We're getting a little bit of buffering of your voice, but I can fill in any gaps that are relevant. So God, I thought I'd been plagued by enough technical problems before, but they keep coming back. I think we're having Skype congestion out there in the real world, not on our links, because both of us have got excellent links. So I think Skype's playing a little bit of hardball with us, because I'm bringing you in from Brisbane via Skype, and I'm here live streaming out to all the different platforms that it's available to me, YouTube, Twitter and Facebook at the moment. Don't seem to have anyone on Twitter by the look of it, but there's a lot of you on this Facebook page, so g'day, big shout out to all my Smart Energy Lab folk. And Bradley's got another question. So Bradley, yes. Could high voltage PV input MPPT DC coupled replace AC coupled inverters? Now it's going to feed in well to what I'm going to do in a minute. So got that question. Could high voltage MPPT DC couple replace AC coupled inverters?
Do you want to take this one or should I?
Well, hang on. Before I go on, I just got feedback from Bradley that there is no freezing. So it's purely on my end. Oh, that's good to know. So what I'm seeing is a little bit of stuttering, but it's actually going perfectly out to the feed. So thanks, Bradley, for the. That's
your computer's processor dying.
That's right. Thanks for the tech monitoring. All the feeds. I think I'll hand this one to you, which is, do you think there is a pros and cons of DC coupling versus AC coupling, and then I'll draw a little picture to explain the two in a minute.
Okay, absolutely. So the DC coupling market is it shifted. It went towards the smaller PV applications, while AC coupling sort of went to the larger mainstream installation. And that was seen in the product development. So you've got MPPTs with very low input voltages compared to AC coupled inverters that can handle very high PV strength. Of that, I think the market got a little bit complacent over the years, so there was not that same level of innovation in the inverter market, and that makes sense though, because it's a smaller market by comparison to Grid Connect. But I think over the next year or two, you're going to see a lot more high voltage MPPT options coming to the market, and they will sort of equalize the I think, especially once high voltage MPPTs have earth fault protection built in, which is not too far away at this point. I should add, this is probably a good time to mention it, but as of Q4 2020, our 48 volt MPPTs, their pricing is being adjusted, so it's actually very, very similar to the price point of the Fronius and Solar Edge AC coupling options. So that's something to keep in mind. If you are doing a AC coupled system and you want to try out DC coupled, there's very, very little difference in it as of Q4 2020. The fact that you're wiring up an extra MPPT as opposed to one inverter, but to be honest, with off-grid, having redundancy is actually a fantastic thing, and it's not something to be overlooked. So it's actually, I think that's probably a benefit from that, because if you got one product, say potentially one product fails, you're not left without any PV input at all. You've still got that second controller there to provide power. Which is crucial when you're in the middle of nowhere, and you can't get something out next day like we can with group stuff. So that's definitely something to keep in mind.
Okay, well, what I'm going to do now is for the audience, we used a few technical terms there, and this is a global audience, and not everyone is into the tech as much as Peter and I am. So I'm going to explain what AC coupling and DC coupling is with just a little drawing. So I'm just going to flick over to my drawing tablet, and let's see if I can bring that up. There we go. And I'm going to bring my picture on screen so you can still see me. Where has that gone? Okay. And bring that on. That's me over there. Right. Okay, so here I am in drawing land. I just realised my phone's over there. It's going to go buzzy. So what Peter can't see this, but everyone else out there in the real world can. What we're looking at is a drawing that I've done beforehand, which I'm going to do some colour on top of just to make it a bit clearer. And it's showing two basic configurations of what is commonly referred to as AC coupling and DC coupling. The thing to remember with the terminology AC coupling and DC coupling is it's about how does the renewable energy get from the PV panels. So this is the symbol for a PV panel down the bottom here. How does it get from the PV panel to the storage, to the battery system, which is over here? It's through an AC network. So I'm just going to draw in brown the AC parts of the system. So here we go. That's our feed coming in from the street, and we've got AC going to our solar inverter. We've also, and it's connected to a dedicated circuit in the switchboard or main switchboard. This is our battery inverter, and I'm using that terminology to sort of differentiate it from a solar inverter, though the symbol's exactly the same because it's a device that converts from AC to DC. And so, or DC to AC, sorry. So,
and DC to AC.
Deliberate mistake there.
I got you.
And of course, the customer's loads are all AC as well. So I call this the house light and power down there. So I'm just showing overcurrent protection as you should. So that's the AC side of things. But of course the DC side is the solar array, and there's the solar array or the battery system. So these are DC. So I'm just going to call that DC and brown for AC. So the coupling of how does the energy get from the orange PV area around through the AC network to the orange battery DC area is through the AC network. So it's called AC coupling. Now what that means is that you could actually start off with just a solar inverter. Let's just hide all that stuff there. So that's your system. You've just got a solar inverter supplying some clean renewable energy to your home, and it works fine. If you want to add storage to this system, you can add in parallel a AC coupled battery inverter. But what you've got now is two inverters, and those inverters have AC ratings. Let's say these are both 5 kilowatts each, which means that you now have 10 kilowatts of inverter power in parallel connected to the utility grid because they are feeding the same connection point. That is an implication which needs to be considered when you get an approval to connect. So when you are adding an inverter onto the utility grid, they will want to go through an approval process. Different states have different rules around this, how it works, and different DNSPs. But effectively, this is limited. You just can't just keep adding inverters and saying, oh, don't worry about it, we're not going to export any, because they do have an impact on the grid itself. So that's AC coupling. Moving over to DC coupling, by contrast. DC coupling, well, here we've got a battery inverter, and it's also, I'm drawing a bit of colour here, connected by an AC circuit to the switchboard. And we've got some light and power for the home here, like that. There you go. So the DC side here is connected to the battery, but the way that the DC PV power, which is over here, gets to the battery is through a dedicated DC connection. So it's coupled on the DC side. So that's DC. Now you'll notice the symbol here for the maximum power point tracker looks very similar to an inverter symbol, but for those who are familiar with it, the little dash lines mean DC, as opposed to the sinusoidal line meaning AC. So this MPPT is effectively a DC to DC conversion device. The reason it converts is it's converting voltage and current to match that of the battery. So the PV array might be working at several hundred volts, whereas the battery might be working at 48 volts. And the magic of the MPPT is it does the maximum power point tracking, but also the voltage matching to suit the load, in this case a battery. So that's DC coupling, but note the difference, only one inverter. You don't have utility approvals for DC coupled side of the system. You don't have to get an approval to put in an MPPT. And what that means in practice is this part of the system is up to you, up to the customer, what they want to install, how much. They're not limited by any rules around maximum inverter capacity. So only one inverter. The DC side is a separate design, but, and this is where Peter will probably reinforce it, you've now got a dedicated way of charging that battery. It's independent of whatever happens on the AC side. You can just take away the grid, you can take away the battery inverter, you'll still charge that battery. So it's got one dedicated purpose, which is to provide clean, smooth, and you'll come to that in a minute, DC power to charge that battery. So going back to you, Peter, I raised a few things there. House, let me bring you back on screen so people not wondering where you're gone. Nearly there. Okay, you're back on. So I used a few terms there like clean, smooth DC power. Now, I know we've talked about this in terms of the advantages of DC coupling.
Big things with DC coupling, because when you're charging a battery from AC to DC, you've got that AC to DC conversion process there, which tends to not produce the smoothest DC power. When you've got a DC to DC source, basically, so you're charging effectively from pure DC, it's much smoother DC power as an end result, because you're not trying to convert it from sinusoidal waves.
Right. So you don't have
with
pulsed
pure DC,
DC,
which is a lot gentler on the batteries.
Yeah. I mean, people think that an inverter is converting AC power to DC, and it's just pure DC, but actually it's pulsed DC, isn't it?
Yes, that's it. Which creates heating in the batteries, and over up to 10 years, sort of depending on the life of the system and the batteries, that's going to actually drastically reduce the life of the batteries. In some cases, some batteries are designed to handle it, and some inverters have very, very smooth charging, but a lot of them don't. And so as a rule of thumb, generally direct DC to battery charging is just far better for the batteries. Creates a lot less heating in them. I see that too. If you put two systems side by side with, say, with SP Pro monitoring, and you're watching the battery temperature, if you have one rate from and one charging at the same rate from AC, you'll see that the battery temperature, provided the cells are almost, you'll see that there'll be a temperature difference there, which over the lifetime of the batteries will have a negative effect on them.
Right. Yeah. So
yes.
Better longevity out of your batteries, a dedicated way of charging them, not limited by utility rules about inverter sizing. There's a lot of pluses to DC coupling.
Yes, and now that we're going to have price parity, there's a lot less sort of roadblocks in terms of why you'd go AC coupling off of DC. But I mean,
price parity as
for example, we don't offer a 6
your
kilowatt
product's
48 volt
capacity versus an AC coupled solution.
Yeah, that's it. That's it. So 2 of our 1.5 kilowatt MPPTs basically as a solar edge, or actually less than a Fronius and slightly just a little bit more than a solar edge 6 kilowatt inverter. So that, really sort of takes away most of the roadblocks with DC coupling, which is quite exciting to see.
Right. Cool. Okay. So that was our little tech bit drawing on how IV curves work and the difference between AC and DC coupling. But I should point out too that you don't have to have just one or the other. You can have both, can't you?
No. For example, what a lot of installers are doing these days is they're feeding the daytime loads with AC coupling and charging the batteries with DC coupling, which I think is a pretty good way of doing it. You're getting the best of both worlds there in terms of efficiency. And it's gentler on the batteries, and you don't actually have to run the battery inverter as hard because you can feed the daytime loads directly to the actual AC side of things, which is a really good solution all around.
Well,
provides black start capabilities.
Yes. Okay. So let me just bring that my little drawing back up again because you've just raised another consideration there, and I'm just going to shrink myself down to the corner there. All right. So you said you could actually have both, and I'm just going to draw that in here. So on our DC coupled side here, I'll just bring it over a little bit more. Yeah. Unless I'm not wearing my sunnies today, but there they are. So there is another circuit which we're going to put a solar inverter on. So we might have started with a DC coupled system, but we choose to add an AC coupled solar system as well in parallel. Now, you mentioned some people choose to supply loads with the AC coupled inverter and charge batteries with the DC. Why was that?
Because it's the best of both worlds in terms of efficiency. You've got the DC being directly fed to the DC batteries, DC being directly fed to the AC loads, rather than going DC to DC for the batteries and then DC to AC to feed the daytime loads. You've got kind of multiple conversions happening there, which is just power losses at the end of the day, and excess load and wear on the actual equipment. So if you design it in a way where you've got the loads, the power going where it needs to go, it's a lot better for the longevity of the whole.
Gotcha. So just to draw that through, during the daytime, the energy from the solar array, so we'll draw a nice yellow sun here, is supplying energy through to the loads in the home. So that's during the day. Now, solar inverters are very efficient, typically in the high 90s, at converting DC to AC. But at the same time the sun's shining, here we go, the sun's shining, and this system is charging the battery. Now, it could do both. It could also supply the loads at the same time, but it might preference charging the battery during daytime hours. Then come nighttime, when the sun has gone down, so it's draw a little moon there. It's now nighttime, so we'll cross the sun out. We'll cross the sun out over here. And now that it's nighttime, we've got nighttime power. So it's nighttime, the power can actually.
So the battery inverter takes over.
That's right. Now the battery inverter is supplying the loads with nighttime energy, and there is only one conversion from DC to AC going on in that time. And of course, the solar inverter can't do the same because it can't work when the sun's not shining. So you're effectively using the two sources at their optimal efficiency.
Yeah, that's it, which is why it makes a lot of sense to do it like that at the end of the day. And it provides additional redundancy to the system as well. Multiple points of failure there that won't really take out your power necessarily, which is beneficial. Dealing with off-grid systems anyway.
Well, I just learned something. I hadn't actually thought about doing it that way, preferencing charging during the day with DC coupling. So, yeah, thank you, Peter, for that idea. That's a great one.
That's all right. Happy to help.
And by having both, it also means you've got that expansion option. You might have started with one or other, but you can add the other if there is space considerations, etc. So you're not locked in. Both AC and DC can cohabitate.
Absolutely. If you you put on another AC coupled inverter. If your nighttime increase, run the charge controller and expand the battery bank. So it's the load is being actually utilised.
Okay. Let's move on to some other material that I wanted to talk about, which is so where do you think DC coupled systems are headed? What's on the horizon?
Okay, so as a sort of industry thing in general, what you're going to see uptake, especially combined with electric vehicles, you're going to see a massive uptake in battery storage. And what it'll probably end up being is your EV or your vehicle or your mode of transport during the day will actually end up doubling as your battery storage during the night, or just while you're not using it or not driving it. Because what the EV industry is doing at the moment is driving the price of batteries down significantly through the economies of scale, point where it's going to make total economic sense to buy a car, use it as $20,000 to $30,000 on a vehicle anyway, and then you just plug it in at night and it powers your house, or you work and charges up off PV during the day, and you get home and you plug it in and powers your house. So it's going to make the economics of large-scale battery storage a lot better when you can just write half of it off effectively. Now, where high voltage DC coupling comes into that is it's a very, these are DC batteries. So DC EV charging is definitely going to become quite a large thing, I think, because it just makes a sense at the end of the day. And especially as the adoption of EV batteries sort of increases. And it's totally necessary because we've got an abundance of EV at the moment, to the point where it's got grid stability issues in states like South Australia. And that would easily be solved by having sort of batteries plugged into the grid, which is what they're looking at doing. But I think EV is a really good pathway for achieving that, because it's going that way anyway. So might as well put it to multiple uses. And I think we will be pursuing that in terms of good, clean, pure DC power to charge these batteries when the time comes.
It sounds like another episode of War of the Currents.
A little bit, yeah. At the end of the day, but DC has already won effectively, because all the high power charging of batteries at the moment is DC. So your superchargers you plug into with your Teslas, it's all DC. They don't high power charge AC. It just burns out the batteries. So if you've got PV and you're charging your car from PV anyway, you might as well keep it DC and there's no point converting your PV to AC and then back to DC to charge your battery. It just doesn't make sense. Kind of like that'd be like using your AC coupling to charge your batteries. It's not the most effective way of doing it. But for that to happen, MPPTs have to be able to hold high voltages. Very, very high voltages. We're talking 1,000 to 1,500 volts. Some standards have to come around for that as well, and to be able to charge the 400 to 800 volts. But everything's going upwards as panel power increases. So we're seeing currents on 48 volt now, anywhere from 80, 100 to 200 amps on a bus, which just you start to get pretty insane cabling requirements at that point, and it just makes total sense to move to a higher voltage. And and off-grid markets, now that we've got really good 120 volt options there, you've got your SB, what they've been doing for yonks, and then you've got your Power Plus offering a really awesome modular 120 volt battery, and we've been doing 120 volt chargers for yonks. And now that the earth leakage standard has changed, a lot of the requirements that were not required on 48 volt previously required on 120 volt is now required across the board. So the barriers to 120 volt are really falling fast.
Okay, so
and as power density in panels increases, it makes sense.
Thanks, Peter. I'm actually going to cross to a question in a minute, but I just thought of something. With the move back towards DC for things like high power charging, wouldn't Thomas Edison be a bit annoyed that he's probably saying "I told you so," because he lost out to Westinghouse when they had the battle of which is the right way to reticulate energy, AC or DC. Westinghouse won out with the AC option. Yeah, so the question that came from Joe is, can we talk about DC isolator selections when regarding a fault to earth? Now, this is not so much, I think I can interpret this question as the fact that you get different pathways in a fault with a non-isolating device such as a transformerless inverter, and that you need to consider the fault path when selecting the equipment and the voltage rating of it. So I'm kind of sort of stepping a little bit away from just talking about DC charge controls for a minute and just answer that question. So thanks for that, Joe. So I'll cross over to my little drawing tablet again, and that gives Peter a chance to have a glass of water. So where's my drawing tablet? It's over there. Okay, bringing that up. And if I can bring myself on there as a little person so you can see me in the corner. And turn that microphone on. Got a lot going on here. Yep. Okay. So Bradley also said when you were drawing on the whiteboard, the mic was too far away, but I think I've moved the mic in a bit. So Bradley, let me know.
That was, you had the other mic on before.
Oh, okay.
I was going to say something.
Does it sound better now?
Thought I wouldn't bother.
Yeah, no, let me know.
That's good.
So I've got so many mics in this room and so many buttons to push. So is this good? You can hear me okay?
Yeah, no, that's good.
Great. Okay. So the question I think that Joe's asking is about voltage rating of DC isolation devices, or in a PV array particularly. And I'm just going to draw a simple PV array here with a single point of isolation. So here's our isolation device here, and it's load breaking, and it's connected to a transformerless inverter. So if you're wondering what a transformerless inverter is, effectively almost all inverters now you are not galvanically separated from the AC side. They rely on their internal electronics to protect against possible earth fault problems, and so they have inbuilt earth fault alarms. So here we go, there's our live. If I've got a nice blue here, here we go, there's our neutral going out this side. I love drawing in colour. And good old MEN to earth down here. So that's our MEN point. So for those who are not from Australia or New Zealand, we have a strange earthing system in Australia and New Zealand called TNCS, which bonds the neutral to earth at the customer's premises at the main switchboard. Now, if we've got an array here operating at, say, let's say it's around 500 volts DC, and someone installing the system or some other creature that's come along has caused a fault, something like a pinched cable, a chewed cable, and it touches onto the earthed array, it will cause an earth fault at some point. So I'm drawing that as a fault to earth. So there's our earth fault at this point. What's going to happen here is that we now have an alternative way of returning that current. So the current can flow through here. Now this is the scary bit, goes through the transformer in the street and all the way back to here. So that's the path of the fault current. And when you go to remove that fault and open the DC isolator at the inverter, the PCE, you're only going to be interrupting that current on one switched leg. And that means that the voltage rating of this product across one switched leg needs to be greater than or equal to 500 volts DC at the current, at whatever the current is of the array. So it's not, many products are rated when both poles interrupt the current, so you've got to look carefully into the voltage rating of the product to make sure that you selected the right one. So I hope that answers your question. Joe?
I might add to that a little bit, actually.
Yep.
That's just got me thinking. For example, in the event on a DC coupled system anyway, actually I think it still applies to AC coupled, but in the event that there's a fault to a PV voltage on the battery side, so if you get the conductor that's not the common in the actual power conversion equipment, so in ours, for example, that would be the negative conductor. If that had a fault to earth, you'd effectively get the PV voltage on the battery side of the system. which is what earth fault protection is designed to prevent. But does that mean all the breakers need to be, all the breakers on the battery side of the system and everything needs to be rated to the same voltage as the PV array is rated to?
Very good question. And actually, my electrician, Anne, she raised this with me the other day. And even though I'm on the standards committee and you think I'd be thinking about this stuff, I hadn't actually picked it up. And so, yes, there is a consideration as how far down the chain does the voltage rating of every component in the system go when you start to talk about non-galvanically isolated devices such as transformers, inverters, or in the case of DC-coupled systems, MPPTs. Is it the DC battery isolator? Is it the battery itself? Does the battery need to be rated to the open circuit voltage of the PV array? I can't give you a quick answer on that one. It may well be that we need some clarification in the standard. We are actually updating 5033 at the moment, which is the PV array standard. 5139, the battery standard, isn't scheduled for an update yet, so it's probably a way off still. So that may be one of those things that industry works out in the meantime as an acceptable solution. And ultimately, for those whose occupation it is to install this equipment, you need to comply with the regulations that in your state electrical regulator will enforce. So if there is any kind of uncertainty about interpretation of a standard, you should check with your state regulator.
Well, that's also just thinking further on that, because that would only really be a problem in systems that are functionally earthed without earth fault detection. Now, if it's a floating system and you've got 2 points of failure, so to actually create a fault, you need both the positive and negative insulation to be damaged and leaking at some point, or connected to earth at some point. Now, the earth guard, the way it works is it effectively detects a fault on a single pole. It monitors each pole individually. So, it's almost certain that you'll pick up the fault occurring on one pole before it's actually alive and dealt. So it'll trigger if the positive insulation is starting to break down, and it's not dangerous yet. It's not actually flowing positive connection to earth, but the negative is not yet connected to earth. So with floating or unearthed DC systems, you've got 2 points of failure there. I think it's probably the sensible solution to this issue, and I think it's only quite dangerous when you don't have earth fault monitoring there and you've already got one pole connected to earth, indefinitely. That would be my take.
Okay. So because I'm streaming to multiple platforms, some people can't see the questions from other platforms. So I've had my first question come in on YouTube, and it's from Noni. Noni says, hi, I would like to know what battery can be used on the Fox ESS 5000 reviewed 4 days ago. Now, I actually typed an answer to this straight away to Noni, but effectively the Fox ESS F5000 is a grid connect inverter. It's got no battery ports at all. But so you can't connect a battery directly to it. There are many inverters on the market which are pure solar inverters, but in an AC coupled system, you can add an AC coupled battery inverter as per the drawing that I did earlier today. So really, you don't actually have to connect a battery directly to an inverter to have storage as part of your installation. I'm just going to cross to that picture so you can see it again. There it is, Noni. So on the left-hand side, it says AC coupled. You notice that the solar inverter here could be a Fox ESS, and the battery inverter could be any AC coupled battery inverter. There are many out there. So you're not restricted to your choices. Okay, so just going back to you, Peter. Peter, we're coming to the top of the hour. In fact, we've just overshot it by a little bit, and so we're going to start moving towards the end here. So we've covered some great material here. Thanks, and thanks to a lot of questions coming in from the audience. That's always good. Lastly, do you have in terms of the future, what's on your future wish list?
Oh, geez. Of course, you've got your high voltage DC there, which that's something we're actively pursuing. But I'm sort of the application of IoT devices, batteries. That's something that we're actively looking into, and sort of how to optimize energy usage. Get everything talking to each other to make sure that we're wasting power. Like, for example, with our factory, where there's opportunities to prevent losses. And, up until recently, we used to high power test all our controllers on lows, but now we're actually high power testing into an actual DC coupled system. So effectively, we're charging the battery up, and then the SP Pros in our system are exporting back to the grid, which is then being drawn in PV simulators doing the testing. So we've actually got a closed loop there with our power for high power testing. So we end up using like less than 100 units at 4, 5, 6 kilowatts, which is really quite awesome, rather than just dissipating that out.
So recycling is core to your business.
Recycling is now, it's core to keeping my power bill down, that's for sure.
I remember someone suggesting making every surface in a home a solar panel so you could recycle the light.
There you go. Well, less recycling and more just preventing power wastage. I get sort of a lot of IoT devices talking to each other and telling each other how much power they're using, and when it's unnecessary, you can work to optimize power in the home. Roll that out on a sort of a massive scale across the grid, and you'll end up actually reducing your power requirements quite significantly, which is exciting and something that will be.
Peter, actually, we've got a sneaky last question for you, came in just then on Facebook, which was how are the PV oversizing limits of the AERL units set? And can you comment on the various sizing limits between brands? Well, we'll leave the other brands alone. How do you set your PV oversizing limits?
So basically, PV oversizing is... on all AERL controllers, it's a 1.4 times allowable oversize. And what the controller limit input power. So we'll put the controller in a less optimal point, like we'll move the MPPT point back closer towards open circuit and run sort of our efficiency to limit the the throughput power in the devices and make sure we're not overpowering the devices or overcharging the batteries. So that's out there. It's done based on sort of what for momentary points in time. So, for example, if the software to react with something and we had a surge through, but close to the full array's power or something, then the device is designed to be able to handle that. A certain period of time, the software can react and limit it. Oversizing sort of figures. We make sure we can handle it, but the software will kick in quickly to reduce power if required.
Yeah. So just for those who are not familiar with this terminology, oversizing, it sounds like you're sort of going to blow something up. But the reality is that every day isn't a perfect sunny day. Well, certainly in Melbourne it's not. Maybe it is in Queensland. Therefore, actually having more peak watts on your charge controller than it can actually convert is not a disadvantage, because you might not have a perfect day. You might be at half solar potential, but your array is bigger and therefore producing more energy. So oversizing actually makes a lot of economic sense for optimizing the production of your system. Yeah. Okay, well, thank you so much, Peter. This has been really interesting for me too. So it's one of the reasons I do these tech talks, is just to learn stuff and to share that with my audience. So thanks for taking your Sunday afternoon off to chat to my audience.
That's all right. It's been my pleasure, Glenn. Anytime.
Okay. Well, I'll just say farewell, and you'll be able to catch up these Toolbox Tech Talks on the various channels on my Smart Energy Lab YouTube channel, on my Smart Energy Lab with an S on the end Facebook channel, also Solar and Storage Trainers, and live on Twitter at the moment. So I've never actually tried to do this, so maybe in Twitter it's stored. But anyway, hope to see you back next Sunday, same time, 2 p.m. here on Toolbox Tech Talk. Okay.